For a number to be a factor of another number, it means that that number must divide the number in question without a remainder. That is, if 4 is a factor of 20, that means that 4 must divide 20 without a remainder. The same idea is what we are bringing into the factor theorem. In factor theorem, if x minus a is a factor, then it means that it divides a polynomial f of x, and there is no remainder. That is, f of x over x minus a gives whatsoever it's going to give, but the remainder is going to be equal to 0. Take for instance, if you have x squared minus 5x plus 6 divided by x minus 3. The normal way we would have done this is to perform a long division. X squared minus 5x plus 6, and here we have x minus 3. Then we say x in x squared is x. Then you go back to multiply that, you have x squared minus 3x. When you subtract, this becomes a negative 2. Let's drop down the 6 right here. Now x divide this as minus 2, and then it goes again to multiply. Minus 2 multiplies minus 3 as plus 6. So when you subtract, you have 0. So in essence, we can say that x minus 3 is a factor of x squared minus 5x plus 6. Now, rather than going through the rigor of long division, since our goal is to know if this expression is the factor of a polynomial, the factor theorem says that, okay, you can take your x minus 3 and set it to be equal to 0, so that you have x is equal to 3. And then your f of x, which is equal to whatsoever it's going to be, the remainder can be obtained by taking f of 3, that is replacing the x by 3. And now you have the remainder. Take for instance, in our case, f of x is x squared minus 5x plus 6. So to know the remainder, we substitute 3 into f of x, right? So we have 3 squared minus 5 times 3 plus 6. So this is 9 minus 15 plus 6. Now this is equal to 0. So with this conclusion of f of 3 being equal to 0, we can say that x minus 3 is a factor of x squared minus 5x plus 6. So the goal is that if x minus a is a factor of f of x, then, when you set x minus a to be equal to 0, you have x equals to a. Then f of a must also be equal to 0. That is, after you've replaced your x with a, your remainder must be 0. Now you can have your factor to be in the form px plus q instead of x minus a. That is, you have a coefficient for x that is not 1. So what you do is basically almost very similar. You take px plus q to be equal to 0, and then px equals negative q, and then x equals negative q over p. So which means that if px plus q is a factor of f of x, then f of negative q over p is equal to 0. In the remainder theorem, however, there is always something left. Let's say you are trying to divide 25 by 4. By the time you are done with this division, you have 6 as the answer, but you're going to be left with 1 as a remainder. So which means if you take f of x and then you divide it by x minus a, you are going to be having a remainder. And that's the idea behind the remainder theorem. So which means that for x minus a, if I take f of a, then my f of a is going to give me an answer that is not 0, which we are going to be referring to as the remainder. So let's say that for x squared minus 5x plus 6, you are using x plus 2 to divide it, like the long division that we did previously. Then it means we're going to be having something like this: x squared minus 5x plus 6, and here we have x plus 2. So when you divide through and through, you have x. This is going to be x squared. This is going to be plus 2x. When you subtract, you have a negative 7x here. If I bring down the 6, and we take x again to divide this, we have minus 7. Now if you multiply back, you have minus 7x minus 14. So when you do that, when you subtract, you have 20. If you compare this to the result that we previously obtained, you're going to see that what we got here when we're discussing the factor theorem is 0. But now we have 20 as an answer. So which means that if I take f of negative 2, remember that this is x plus 2, we set it to be 0, and then we have x equals to minus 2. So if we set f of minus 2, we're going to be having minus 2 squared minus 5 times minus 2, then plus 6. So here we have 4, here we have minus 10, and here we have 6. Oh, sorry, plus 10. So the answer here is 20. So again, rather than going through the rigor of long division, just obtain the remainder, you can apply the remainders theorem by direct substitution, and then you have your answer. Also, if px plus q divides f of x, that is f of x divided by px plus q, and you want to know the remainder, remember that is going to be f of negative q over p, that is by setting px plus q to be equal to 0, and then x equals to negative q over p. You're going to be having your remainder right in front of you. Now let's take some questions. The first one says we should determine whether x minus 2 is a factor of x squared minus 4x plus 4. So we know that from here, our f of x is x squared minus 4x plus 4. And now we want to know if this is a remainder. So, of course, we're going to take f of 2. Remember, it is x minus 2. Set x minus 2 to be 0. You have x equals to 2. And then you set that as f of 2. Then you substitute. So you have 2 squared minus 4 multiplied by 2, then plus 4. So here we have 4 minus 8 plus 4. And this is equal to 0. Therefore, we can say that x minus 2 is a factor. In the second instance, however, we are to state the remainder when this is being divided by this, this, and this. So for the first one, we have f of x to be equal to x cubed minus x squared plus 3x minus 2. So for x minus 1, we are going to set f of 1. So when you do that, you have f of 1 equals 1 cubed minus 1 squared plus 3 times 1 minus 2. 1 cubed is 1 minus 1 is 1 squared plus 3 minus 2. So 1 minus 1 is 0 and 3 minus 2 is 1. So the remainder in this case is 1. In the second case, you have x plus 2, so which means you are taking f of negative 2. And that's going to be equal to 2 cubed negative minus and plus minus 2. So this equals to minus 8 minus 2 squared is 4, then minus 6, then minus 2 again. So this is negative 12, negative 18, negative 20. In the last one, we have 2x minus 1. Remember that if you set 2x minus 1 to be equal to 0, you have 2x equals to 1, x equals 1 over 2. So which means our goal is to set f of 1 over 2. Okay, that's equals to 1 over 2 raised to the power of 3 minus 1 over 2 squared plus 3 times 1 over 2, then minus 2. This is equal to 1 over 8 minus 1 over 4 plus 3 over 2 minus 2. I'm just going to do it the whole way to find the LCM, and then I have this as 8. So it's going to be 1 minus 2 plus, this is 12 minus 16. 1 minus 2 is negative 1. Negative 1 plus 12 is 11. And 11 minus 16 is minus 5 over 8. So which means that the remainder after 2x minus 1 has divided x squared minus, x cubed minus x squared plus 3x minus 2 is negative 5 over 8. You can give this question a try. You can pause the video and do that. So I'm going to solve the problem now. We're trying to see the remainder after this has divided this. So we need 2x plus 3 equals 0. You have x equals negative 3 over 2. Then we need f of negative 3 over 2. And when you substitute that, you have 2 multiplies cube minus negative 3 over 2 squared minus 5 times negative 3 over 2, then plus 1. So here we have 2 multiplying minus 27 over 8 minus, here we have 9 over 4, and minus multiplies minus, you have a plus, then you have 5 multiplies 3, 15 divided by 2 plus 1. So this 2 divides this, so we have negative 27 over 4 minus 9 over 4 plus 15 over 2 plus 1. So what I'm just going to do here is, here is going to give me minus 36 over 4, and here we have 7.5 plus 1, that gives 8.5. So when you divide this, you have minus 9 plus 8.5. So this gives minus 1 over 2. So whichever method you have used in evaluating this, just make sure that your answer is equal to minus half. Therefore, the remainder when this has divided this is equal to minus half. Thanks for watching.